I think we'll introduce Kai, Peg, well, for our friend later, before we get to the main presentation. But we just want to kind of talk a little bit about the videos that we just saw, we basically look at two different kinds of common arguments for God, from arguing from science. And the first one we may call, sometimes it's called a cosmological argument. Cosmological arguments argue that, well, everything has a cause, and some things don't just pop into existence. It comes into existence because there's a certain cause. And the particular kind of cosmological argument being presented in the video was popularized by the apologist William Lane Craig. It's called a Kalam cosmological argument, and from Arabic. Specifically, the idea was, if you have things, when it began to come into existence, there must be a cause. So I actually want to spend some time to talk about that. I mean, first of all, it seems to be that all kind of cosmological arguments is based on this very basic idea, causality, right? Is that a right assumption? I mean, we have to assume causality before we can even talk about cosmological argument.
Who is a physicist? Knowing quantum mechanics?
No, that's my worst part. That's why I become a software engineer after I graduated.
Because it's a little bit washed out in quantum mechanics.
Right.
It's redefined. Okay.
So from a physicist's point of view, the modern quantum mechanics
has some interpretation about causality not being immediate. But still it's an accurate theory, which is the miracle, which is where evolutionary our brain is not made for.
Yeah, I think the causality, especially in biology, a lot of people just think just developed and everything doesn't go where it's supposed to be, it just goes where it fits best and adapts to this niche. And then by mutations or whatever that are randomly coming without a cause, it might be not fit anymore for this niche, and it's a new niche. So that's, I think, the common thought in biology. And a lot of biologists say it's just this without anything behind it or any intelligent being.
With the cosmological argument, something that's recently, well, maybe not terribly recently, but something that's been voted against that is actually the entire notion of the Higgs boson. You guys have heard about the Higgs boson. It's often called the God particle. And my own understanding of it is very limited. Perhaps after I take a stab at it, Dr. Becker will enlighten us much more than what I know. But basically, the excitement about the Higgs boson is that it's a particle that theoretically could kind of come into existence without a cause. And this would happen through something that physicists call spontaneous symmetry breaking. And the problem that I've found in the small amount of research I've done into spontaneous symmetry breaking, the idea is basically that you have a state of vacuum, nothing in existence, that's in an unstable equilibrium. And so if anything were to disturb that, all of a sudden matter would kind of pop out of nothing because it's a more stable configuration than for there to be no energy and no matter in that space. And that the problem I see with that is any instance of supposed spontaneous symmetry breaking that we could have observed, by the very act of observing it, we are affecting the system. And so I don't believe we can rightly say that we can prove any such thing as spontaneous symmetry breaking, because by observing it, we've affected the system. And so it may not have been spontaneous, it may have been caused by our observation of it. So if there were a universe in which nothing exists, no observers exist, although it's an interesting theory, there is no evidence that physicists have right now that spontaneous symmetry breaking could have explained the start of the Big Bang or the start of the universe. Something that a theory I've thought was very interesting, and I don't know who maybe first could be credited with it, but the idea that, well, if you could explain the Big Bang and the start of the universe with the Higgs boson and the symmetry breaking, but rather than having it spontaneous, recognize that there needed to be something there to give it a little bit of a nudge, and we might there see the finger of God.
Rebecca, want to jump in? Or?
Actually, you really want to know about the Higgs boson. I was chasing for it myself. and we were shortchanged at Geneva until it was painfully established later. The way this goes is, yes, there was a beginning. Yes, the beginning slid into the Higgs field, permeating all space, which then must have a quantized form of it, which is the Higgs boson, which is needed to establish that this Higgs field really permeates the space. This Higgs field created the first set of particles, but not the one you are made of. They are made by caught kinetic energy in the quarks. So, over my life, I was privileged to see the smallest and the biggest. The smallest was at the beginning of my studies. I chased the size of the electron, which turned out to be exactly 0. And it was predicted by this guy, Mr. Feynman, how often you would create an electron and an anti-electron. Some other people measured it wrong, but it was right. So here we have a particle which has no spatial extent. We are made out of it. And the laws of Feynman simplified apply. So that was great. But what does the Higgs has to do with it? The Higgs field is responsible for forming all these quarks. And 3 of these quarks make a proton, which is your hydrogen in your body. The quarks are pretty light, so most of it is their internal motion within the proton. You don't notice that. The symmetry breaking is not the cause. It comes for further development to feed in electromagnetism. You all believe in electromagnetism, and you know the quantum of electromagnetism, like the Higgs field has a quantum, which is a Higgs particle recently found. It's the quantum of the electromagnetic field. It's all photons which rain down on you right now. So if you discovered that, you discovered electromagnetism from the field dimension. Okay, I don't know. You ask.
Feel free to jump in if you hear something you don't understand, which that may take an hour.
If I get carried away too far, sorry.
Yeah, well, I mean, if I may bring it back a little bit, just like on this idea of causality, my layman understanding is part of the reason why we like special relativity, like limit the speed of light is like if you go beyond the speed of light, that observer go beyond the speed of light. There's a sense that you are traveling back in time. And but now the one of the things that people are talking about these days is this entanglement idea. The action at a distance, and it is almost like the effect of traveling faster than the speed of light. And it like how would we look at that?
I don't want to disappoint you, but we create particles all the time in accelerators. One of these particles is called pi0. All right, it decays into 2 photons, which go this way. So if I measure the polarization of this one, I know what the polarization of the other one is. So disentanglement means I knew something about the origin of the particle. So in that sense, disentanglement is to me not so frightening. We work with it all the time.
Okay.
So things are entangled if you know where they come from.
I don't know if you guys have any questions on that, but like in the interest of, please feel free to jump in if you have. No, okay. But in the interest of time, we actually want to like change the topic a little bit back to the fine tuning, which is kind of like another hot topic we discuss these days. Just like obviously, we picked two videos, not so much from, at least from a theist point of view, or even certainly not a Christian point of view, one by a Stanford professor, Susskind and Richard Feynman. So I'll just like give it opportunities for you guys to jump in and like comment on what they say. First, like the cosmological, like the Susskind and what he said.
There is an irony to the whole thing. This lambda from Einstein, he considered his biggest mistake. So, ironically, he didn't know about that.
That's the cosmological argument. Yeah.
The cosmological.
I mean, the constant, that's what.
This constant, which is 10 to the 123 accurately small, 2 times that. So Einstein himself wrote down equations, and then he thought it must be like that, and then he said, oh, that was my biggest mistake ever. And then it turned out if you put it on the other side of the equation, it made sense. So that's the history of this cosmological constant fine-tuning. But the fine-tuning, do you understand it? What these guys are bickering about? What is the big deal? I usually do it in a simpler form. Imagine the electron charge was not 1.6 times 10 to the minus 19 coulomb, as you learn in 802. Imagine it was 2 times 10 to the minus 19 amp seconds. What would happen? Just a little bit more charge, right? Not quite yet. It just makes a narrow circle, perhaps. There are no circles, excuse me. But it would mean that your DNA would form. Already that would be the consequence. So all these wonderful possibilities Susskind was talking about wouldn't exist. And that's already one consequence of this fine-tuning. Nobody knows why the electron charge is what it is. Nobody knows why the proton has exactly the opposite charge to neutralize everything. So this is a constant of nature. We don't understand it at the moment. And so...
Is there any way for us to even experimentally find out if there is this idea of megaverse or multiverse, even if, because we are locked into our own universe, right? I mean, can we even...
I've read a little bit about the inverse theory, and Stephen Hawking is a big proponent. I think he's written at least one book, is that correct? About inverse.
Yeah, he is for it at the moment. He changed his mind.
Oh,
Imagine that.
All right, they do that.
I've read a number of quotes from physicists who disagree with Stephen Hawking just on the grounds that they say there is no, empirical evidence for the inverse theory. There's no experiments that back it up at this point.
Well, if you take a look at the most distant galaxy, which is probably far enough that some of those constants might have changed a little bit. But if you look at how the burn, how the electrons vibrate, they appears to be quite constant throughout our observable universe, which is 13 point something billion light years across. So, at least in
Something to
now,
say? Do you have something to say, Joe?
Well, I first of all wanted to clarify if the megaverse theory is this. It seemed to be different than the multiverse.
Please call it a hypothesis.
It's not
Okay.
here yet.
Okay. Because to me it seems to be, and I'll tell you right up front, I'm not a technical guy at all. So I'm your average layperson trying to understand, the most of the concepts of science in general. But as he explained it to me, there seems to be a stark difference in that the multiverse, there could be no way to determine it because it would be parallel to this universe, and we can't go outside. Theoretically, I guess we could somehow go outside of our universe in possibility, but that this megaverse is different. That's how I took it, in that the universe is so large that these different physics universes are within our universe. So then that leads me to the automatic question of, has anybody ever observed that? Is there any empirical evidence to it? And even if there was, then the next thing that comes to my mind is then the speed of light could be different, couldn't it? And if the speed of light could be different, which I think there's some hypothesis that the speed of light has slowed down, then the age of the universe could be drastically different than what it is. So I see that as being a kind of a two-sided issue. Is that, first of all, is there any empirical evidence? Has it been observed anywhere that these constants are different? And if there are, wouldn't that have other implications for the universe we do live in?
To me, the two expressions of it, it's basically the same theory, whether they express it as, it's somewhere out yonder, or else it's existing right next to us. In both cases, there are other existences that we have no way to interact with, no way to measure, no way to experience, or gather data from. And so it doesn't matter to me whether they say it's a trillion light years away, or whether it's existing like in parallel, somehow occupying the same space that we are. But
I'm not an expert on that. I'm a humble physics experimentalist. And as long as there is no experiment which proves that, I consider this a speculation.
Dr. Becker always remind me that his job is like a murderer, right? He kills a theory.
You see, I went through so many experiments, and there are usually 100,000 theoreticians inventing something to fit it, but only one or none would be right. What do you do with the rest of them? That's their problem.
John has something to say.
It seems like one of the challenges of being an apologist, speaking to a scientist, is that every criticism an apologist will have for a scientific positing, theory, hypothesis, whatever, new creative idea, is the word yet.
Yeah.
All we can say is it hasn't been proven or disproven yet, as an apologist.
yeah.
So we have to deal with that.
there are some theories or hypotheses which can be disproven.
Yes.
There are some things which are maybe impossible to prove, and there are some things which may be impossible to disprove. But there's a great number of things which
The
are
dilemma is,
impossible.
you can't prove what you just said is true yet.
Well, there are
All the
I mean,
proofs haven't been attempted yet.
If you take the basic tenets of mathematics as true, then there's a great deal of things in this universe which we can disprove. It's far more easy to disprove something than to prove that it's true.
No, I'm not disputing that some things have been disproven. What I'm saying is that not everything has been disproven that we would disagree with.
Well, that's correct.
Yet is a big word for the apologist,
Well,
speaking to the scientist. You can't say that yet.
I don't know whether this contributes to this discussion, but when I started in physics we knew what Feynman said was true and it worked out and everything was fine. In the 55 years I've done physics, I have lost a lot of my certainty. And that's probably why I'm sitting here. And even discoveries which lead to Stockholm doesn't cut it. The quantum mechanics question is very bad because you know the Schrödinger cat, whether it's alive or dead. That's the one which doesn't fit our brain. So we should be very humble about that we say this is true and this is false. Because the wave function contains both. And that's what the quantum encryption in future will be. We have a quantum computer in Unilab which can do some thoughts much faster, but it is not the true-false dialectic. So our logic is very bad due to this kind of discovery. The other bad thing about philosophy is the uncertainty relation. The uncertainty relation has killed the Laplace demon that you ever, with a supercomputer, can calculate the future. It will sooner or later derail. So, in my lifetime, I've learned to be much more humble about what we observe and whether our logic is the true logic.
Well, that gets into the realm of philosophy and metaphysics and epistemology. And I think that, like, to kind of wrap things up before we go to Kai, I just like want a quick comment from you about the comments made by Richard Feynman. Like, he has a pretty agnostic attitude towards like everything, basically, especially religion, I suppose. Like, he thinks that that's the only way that you can be a scientist is to be not take any a priori answer for granted.
Well, I guess physics is a little bit different than, my background, biology, because in physics you have theories, and then you find out evidence for this theory, and then it might even make it into the physics books. And then maybe 20, 30 years down the line, there's another smarter person or a person that thinks very differently and finds
Just as more
actually-
evidence.
Yeah, gets more evidence to this, or actually finds evidence for something the opposite maybe. And biology, on the other hand, that's why I like biology. You basically look at things, you discover things, the DNA, proteins, you look at them, and they are there. We don't need really theories. As technology evolves, we can look at more detailed aspects of proteins or whatever. And that's why I, to bring this back to God, see myself as somebody who takes what God created and just discover how amazing it is. And it's so detailed and on the razor's edge and everything, and even in small, my field is bacteriology, so I'm dealing with bacteria who are even so much smaller than human cells, mammalian cells. And it all works so perfectly. These little things can survive and they can make us sick, and this is a bad thing, but they also do a lot of good things in helping us digest food or whatever. And this is so, for me it's amazing to see this little compartment of a bacterial cell that's going on there.
Early?
Well, I started with the size of the electron, and then I migrated up to what comes out of the universe to the space station. So I was privileged to see that, and I must say it has deepened. First of all, it has made me much more humble in my arguments, and on the other hand, I think, would you believe in a God whom you could understand? greater than everything. And I don't know whether you remember Victor Weisskopf, one prominent MIT physicist. He was once asked this question and he said, "Oh, I give you the answer the old Jewish rabbi has given me. God is so big he doesn't even have to exist." By which he meant, in your brain. Because your brains are kind of confined to the 3 dimensions with the time we live in. How do you know there is not another dimension and you only see the shadow of it? How do you live in a universe which has black holes where time stops? There's no time, it's pierced in the middle of our Milky Galaxy.